Okay, Assalamualaikum. Inshallah, today we are going to continue with our chapter 2 for CSC580. Okay, in this chapter we are going to investigate about the parallel platform. Yeah, dalam parallel processing. Alright, so parallel platform. Implicit parallelism, trends in microprocessor architectures. So apa dia implicit? Alright, first thing first, sebab kita kata kat sini implicit. So what is implicit? Implicit, kalau okay, siapa yang sini banyak dengar Spotify, contoh dia, right? Kalau dalam Spotify dia akan ada certain songs yang dia akan mark as explicit. Meaning apa kalau explicit? Explicit meaning dia tak cover. Maksud dia lirik dia macam terus terang kan, nak maki contoh, right? So yang tu adalah explicit. What about implicit? Implicit meaning dia secara sembunyi. Maksud dia most user tak perasan pun benda tu, right? So yang tu apa yang terjadi dalam kita punya microprocessor. So in microprocessor, clock speed have posted impressive gain over the past 2 decades. So 2-3 times of magnitude yang kita discuss dalam first week punya lectures. So higher level of device integration have made available a large number of transistor. The question is how best to utilize this resource is an important one. So current processor use this resource to multiple functional units and execute multiple instructions in the same cycle. Yang ni adalah implicit parallelism. Maksudnya dalam satu clock cycle tu dia buat banyak-banyak functional units. So dia parallel secara tersembunyi, dia tak secara explicit. The precise manner in which these instructions are selected and executed provide impressive diversity in architecture. So kita tengok pipelining and superscala. Pernah dengar tak pipelining? Pipelining macam mana? Pipe air. Okay. Pipeline maksudnya pipe. Maksud dia ada pipeline ni daripada air keluar sampai air. Daripada air keluar, air masuk sampai air keluar. Contoh dia, technique used in the design of computers to increase their instruction throughput. The number of instruction can be executed in a unit time. Maksud dia macam mana kita nak so that kita punya proses tu speed up daripada satu habis, satu pula yang akan keluar. Contoh dia, the basic instruction cycle is broken up into series called pipeline. Rather than processing each input sequentially, one at a time, finishing one instruction before starting the next, each instruction is split up into a sequence of steps, so different steps can be executed concurrently at the same time in parallel by different circuitry. So macam mana rupa pipelining ni? Okay, kita tengok macam ni. Contoh dia macam ni. Right, so we divide it into 5 different stages right here. Okay, when we have 5 different stages, contoh dia kat sini one instruction 1 habis, instruction tu pula akan buat final function and akan habis. Lepas tu pula kita tengok yang 3 pula akan habis. Compare to if kalau kita buat contoh instruction 1 perlu buat all 5, habis all 5 barulah instruction tu kena masuk. Maksud dia meaning habis ni barulah instruction tu akan buat dekat sini. So try imagine how long would that take? Kan? That would take a very long time to finish. So kalau tak macam ni, satu clock cycle akan habis satu instruction, dan satu clock cycle lagi akan habis satu instruction. So tak perlulah kita habiskan semua ni, barulah satu lagi akan masuk. Yang ni we call this as pipelining. So each instruction is split up into sequence of dependent step. The first step is always to fetch instruction sampailah ke write back. Okay. Dan contoh lah, yang ni contoh sebab semua different microprocessor different dia punya pipelining. Okay, so pipelining lets the computer cycle time be the time of the slower step and ideally lets one instruction complete in every cycle. So macam mana rupa dia? Lebih kurang macam ni contoh dia. So we have this pipeline untuk buat kereta, contoh dia kan. Okay, so yang ni contoh dia akan pasang pintu, yang ni pasang meter ke, yang ni pasang tayar ke. Okay, contoh dia. So lepas habis je pasang pintu, kereta tu dah boleh siap, contoh dia. Tak payahlah tunggu the whole thing siap barulah satu lagi pula kereta yang akan masuk. So every cars need to go different step. Each robot in the production line has specific tasks, and notice how each robot is occupied, meaning that none of them is idle. Yang ni paling penting kalau dalam parallel processing. Contoh dia, kalau kita ada 4 processor, kita nak pakai semua sekali. Okay, resource dia contoh. Yang tu dalam ni lah kita punya course ni. Right? Pipelining, however, has several limitations in the sense that the speed of pipeline eventually limited by the slowest stage. Kalau ni samalah macam buat assignment kan, contoh dia. Kalau buat assignment last sekali, paling slow adalah untuk tulis report. So nak tak nak, laju macam mana pun, tulis report slow, so slow lah awak punya assignment. For example, for this reason, conventional processor rely on a very deep pipeline, sampai ada yang 20 stages pipeline in the state of the art Pentium processor. back then state of the art. Yang ni dah kat sini tak ada dah. Right? Kita dah tak pakai dah Pentium. However, in typical program traces, every 5 to 5th to 6th instruction is conditional jump. This require very accurate branch prediction. Kenapa perlu jump ni? Contoh dia, tak semua functional unit tu kita kena pergi. Kita boleh lompat. Contoh dia, bila dah habis ni meaning, it is completed. So, it can jump towards another punya function. So, tak perlu go through every single functional unit yang ada. So, contoh dia. Tapi yang ni kena ada branch prediction. Sebab kita nak predict dia duduk mana apa semua. The penalty of misprediction grow in the depth of pipeline since a larger number of instruction will be flushed. Maksudnya kalau pipeline tu silap, itulah kena flush lah semua instruction. One simple way of alleviating this bottleneck is to use multiple pipeline. Ini kita akan tengok next. The question that become one of selecting this instruction. Okay, ingat tak kita kata nak tambah pipeline. Kalau pipeline satu, setiap satu clock cycle kita boleh buat satu functional unit. Okay. Tapi kalau multiple pipelining, kita panggil dia super skala. Okay. Kita pakai ni untuk instruction level parallelism and therefore faster CPU throughput than would otherwise be possible at given clock rate. A super skala processor execute more than one instruction during a cycle by simultaneously dispatching multiple instruction to different functional units in the processor. So instead of buat satu-satu, yang ni dia buat banyak-banyak sini. Sebab kita ada dua pipeline sekali jalan. Right? Contoh dia macam ni, instead of satu kereta siap tadi, kita boleh siap dua kereta dalam satu-satu masa. Right? Yang ni adalah multiple pipelining ataupun kita panggil dia as super skala. Instruction are issued from sequential instruction stream. CPU hardware dynamically check for data dependency. Kenapa? Kalau contoh, instruction A dengan B ni ada data dependency, perlukan satu siap baru dua boleh masuk, meaning dia tak boleh schedule, dia tak boleh duduk sekali. Alright? So we have to bear that in mind. Kenalah kita schedule so that yang ni instruction 1, so yang ni bukan instruction 2, yang ni instruction 3 contoh dia. 2 akan buat dekat belakang belah. Okay, sebab dia perlu result daripada yang satu. So contoh, so untuk buat super skala ni dia punya scheduling is very complicated. Scheduling tu in a sense dalam komputer punya hardware, dalam CPU punya hardware, bukan dalam software. Right, the CPU process multiple instruction in per clock cycle. Scheduling of instruction is determined by number of factors. So we have true data dependency. The result of one operation is an input to the next, just like the example I've given you before. Okay. Resource dependency meaning two operation require the same resource. Maksudnya dia perlu resource yang sama, output daripada sini ke apa semua, output daripada A dia perlukan ke B contoh dia. So resource tu nak pakai, so tak boleh schedule sama-sama. Then kita ada branch dependency. Scheduling instruction across conditional branch statement cannot be done deterministically or a priori. Yang ni maksudnya apa? Branch dependency ni maksudnya kita tak boleh nak macam mana? Kita tak boleh nak conditional branch statement tu cannot be done earlier. Kita waktu run baru kita boleh tahu apa yang jadi apa semua. Itu kita panggil branch dependency. So the scheduler is a piece of hardware, looks at large number of instruction in an instruction queue and select appropriate number of instruction to execute concurrently based on these factors. So scheduler is the most important aspect in super skala. The complexity of this hardware is an important constraint of super skala processor. So super skala execution, kita tengok issue mechanism. Issue mechanism ni macam mana? Macam mana kita nak issue kita punya instructions untuk satu-satu time. In the simpler model, instruction can be issued only in order. Maksudnya in order ni kita habis satu, baru kita bagi yang baru. That is, if the second instruction cannot be issued because it has data dependency on the first, only one instruction is issued in the cycle. This is called in order issue. Maksudnya kalau kita tengok data dependency tak ada apa semua, baru kita hantar satu-satu. So it did not create a lot of problem lah kat sini. Tapi in terms of performance, it is very limited. Right? Sebab apa? Sebab in the end jadi macam satu-satu juga lah. Right? In a more aggressive model, instruction can be issued out of order. In this case, if the second instruction has data dependency with the first, but the third instruction does not, the first and third instruction can be co-scheduled. This is also called dynamic issue. Maksudnya satu dengan dua tak boleh co-schedule. So kita akan co-schedule instruction 1 dengan instruction 2. Right. Okay, so tak payah tunggu instruction 2, tak payah tunggu instruction 3. Contoh dia. Right. So we call this dynamic issue. Performance of in order generally limited. Sebab in the end dia still buat satu-satu. Okay. Efficiency consideration. Not all functional unit can be kept busy at all time. Betul? Sebab kita tengok kat sini, semua functional unit tak adalah most of the time dia akan busy, kecuali waktu part ni dia semua busy. So If during a cycle no functional units are utilized, this is called as vertical waste. So vertical waste adalah yang ini. This one is vertical waste. So some of the functional issue tak digunakan, right? That one is vertical waste. If during a cycle only some of the functional issues are utilized, this is referred to as horizontal waste. Okay. Yang ni pula adalah horizontal waste dekat tepi ni. Sorry. Pening dah. Okay. Dekat sini adalah horizontal waste. Waktu ni tak digunakan. Yang ni adalah horizontal waste. So vertical, horizontal waste. Right. Okay. Due to limited parallelism in typical instruction traces, dependency or inability of the scheduler to extract parallelism, the performance of superscala processor is eventually limited. So conventional microprocessor typically support 4-way superscala executions. Alright, kita tengok kat sini pipelining and superscala execution. So ini adalah horizontal waste, ini adalah vertical waste, for example. So ada lagi satu cara, instead of macam kita buat dua sekali, contoh dia, kalau satu instruction tu needs more resources, kan, needs more clock cycle, so kita boleh tambah macam mana? Instead of kita tambah dua sekali, kita boleh tambah satu function tu saja, macam ni, contoh dia macam ni. Function ni memerlukan banyak, so kita hanya tambah yang 4 ini saja. Okay, execute 3 operation, yang ni saja kita tambah, instead of buat 3 straight, kita tambah yang perlu saja. We call this as VLIW, or very long instruction words. So very long instruction word refer to processor architecture designed to take advantage of instruction level parallelism, whereas conventional processor mostly allow program to only specify instruction that will be executed in sequence. VLIW processor allow program to explicitly specify instruction that will be executed at the same time, which is in parallel. Hanya selected saja yang kita pilih untuk perform in parallel. Kalau tak macam superscala, main kita panggil apa? Main pukul rata je semua. Keluar dah Penang kan, pukul rata je semua, right? So kalau VLIW, kita pilih satu je, kita tambah dia punya functional unit kat situ, right? So this type of processor architecture is intended to allow higher performance without inherent complexity of some other approaches. So the hardware cost and complexity of the superscala scheduler is a major consideration in processor design. Okay, to address this issue, VLIW processor rely on compile time analysis to identify and bundle together instruction that can execute concurrently. So dia punya problem pula VLIW ni, dia perlu compiler yang bagus. Sebab apa? Sebab kita nak kena compile with instruction yang patut buat selepas yang the next, sebab ada yang 3, ada yang 2 and so on, right? Yang ni adalah VLIW, very long instruction word. So for very long instruction word processor, okay, we need a very long compile time to compile this instruction. So daripada segi compiler dia problem yang ni, tapi yang kalau superscala daripada segi scheduler. So these instructions are packed and dispatched together, and thus the name very long instruction word. So VLIW consideration, issue hardware is simpler, but compiler has bigger context from which to select core schedule. Instruction and compiler, however, does not have runtime information such as cache miss. Scheduling is therefore inherently conservative. Branch and memory prediction is more difficult. VLIW performance highly dependent on the compiler. So compiler yang paling penting kat sini, a number of techniques such as loop unrolling, speculative execution and branch prediction are critical. So typical VLIW processor have limited to 4 to 8 way parallelism. Right, this is VLIW. So to sum up previously, okay, kita ada pipeline, kita tengok pipeline. So pipeline untuk improve dia, kita ada superscala, okay. And alternative towards the superscala is VLIW, right? So kita dah tengok 3 jenis implicit parallelism dalam kita punya processor, right? So yang ni dia punya difference, okay. This one is skala ataupun kita panggil dia pipeline, basic pipeline. Ini adalah superscala, dan ini adalah VLIW, right? Okay, dan kita tengok daripada segi limitations of memory system performance. Okay, memory system and not processor speed is often the bottleneck for many applications. So yang ni sebab apa saya keep on tanya kalau dalam kelas tu lah, kelas ODL ni saya tak boleh tanya sangat, so saya agak geram kat situ. Tapi last week kita ada tengok pasal computer specs, betul tak? So computer spec, one of the most important specs that saya nak tengok adalah daripada segi memory. Why memory? Sebab memory is the second most important things in our computer behind CPU. So CPU, lepas tu kita ada memory. Actually dua-dua ni sama penting lah. Just daripada segi speed, okay, CPU paling laju. Second paling laju adalah memory. So data akan feed ke memory, baru akan ke CPU. So therefore, macam mana nak feed data daripada memory ke CPU, that is very very important, right? So memory system performance is largely captured by two parameters, which is latency and bandwidth. So the latency is the time from the issue of memory request to the time of the data is available to the processor. Request bila sampai kat processor bila, that is called latency. Sama lah kalau siapa main game, contoh dia main apa, main PUBG ke, okay, klik shoot tapi dia tak shoot, meaning dia ada dia ada lag. Kita panggil lag itu adalah latency. So sama juga in this case, contoh dia kan nak tembak orang, contoh dia dah aim, tembak tapi tak keluar peluru, yang tu adalah lag kan, ataupun skill tak power, tu lain cerita lah, tapi contoh dia yang tu adalah lag sebab internet connection slow ke and so on kan. So sama macam yang tu juga. So memory nak feed ke CPU, berapa lama daripada memory nak ke CPU, we call that as latency. Macam mana lah bandwidth? Bandwidth macam mana lah? Bandwidth is the rate of which data can be pumped to the processor by the memory system. Berapa banyak sekali pump data masuk ke dalam CPU, yang tu adalah bandwidth. So latency daripada time, daripada memory request sampai data available. Bandwidth pula berapa banyak yang boleh masuk dalam daripada memory ke CPU. Okay, it is very important to understand the difference between bandwidth dengan latency. Consider the example of fire hose. If the water comes out of the hose 2 seconds after the hydrant is turned on, the latency of the system is 2 seconds. So once the water start flowing, if the hydrant deliver water at a rate of 5 gallons per second, then the bandwidth of the system is 5 gallons per second. So if you want immediate response from the hydrant, it is important to reduce latency. If you want to fight big fires, then you want high bandwidth. So ini adalah the difference between bandwidth and latency, right? Okay, so kita continue lagi, improving effective memory latency using caches. Caches ni apa? Cache are small and fast memory element between processor and DRAM. Macam saya cakap tadi, memory nak feed ke processor, adakah dia feed terus macam tu? Actually, dalam processor ada cache. So kalau tengok hari tu dekat CPU Z yang saya minta install minggu lepas, last week, awak boleh tengok setiap satu processor kita ada L1 sampai L3 cache. So dia ada label cache kat situ, right? Cache ni apa dia? Dia akan terima data daripada memory. If a piece of data is repeatedly used, the effective latency of the system can be reduced by the cache. Contoh dia, dalam cache pernah ada data, okay? So latency boleh kurang sebab kita dah tengok, oh data tu dah ada, so tak payah feed in daripada memory ke cache. The fraction of data references satisfied with the cache is called cache hit ratio. Maksud dia kalau cache kena, cache hit. Kalau dalam cache tak ada, kita panggil dia cache miss, okay? So cache hit maksud dia bila processor nak ambil data, tengok dalam cache dah ada, meaning cache hit. Kalau processor nak ambil data, tengok dalam cache tak ada, kita call dia cache miss. So cache hit ratio achieved by ecosystem often determines its performance. Cache hit are served by reading from the cache, which is faster computing result from reading a slower data. Thus, the more requests can be served from the cache, and the faster the system perform. To be cost effective and to enable efficient use of data, caches are relatively small. Cache kita kalau tengok dalam 2MB, 4MB, okay, 16MB, paling tinggi pun 32MB ada kot. Kita tak ada cache 2TB. Sebab apa? Memang tak possible lah untuk buat benda tu. Nevertheless, cache have proven themselves to many areas of computing because access pattern typical to computer application that exhibit locality of reference. Locality of reference yang saya cakap tadi lah, kalau data tu dah pernah ada, so dia akan lebih cepat. So moreover, access pattern exhibit temporal locality. If the data is requested again, that has been recently requested already. Spatial locality refers to request for data if the data is already exists within the cache. Alright, so yang ni tak habis dia punya ayat kat sini, dah berapa tahun dah setelah ini ayat tak habis, saya tak adjust pun, mata betul pakai. Okay. Tapi kita tengok kat sini temporal locality, kalau time ni time, okay? Maksud dia sebelum ni pernah pakai, sekarang tiba-tiba nak pakai, so dia boleh laju. Spatial locality pula, kalau kita nak cari benda tu, kalau dia dah ada dekat situ, kita boleh terus pakai. Kalau dia tak ada kat situ, kita tak boleh nak pakai, kita kena minta dulu. Okay, yang tu adalah spatial locality. Daripada segi time dengan spatial locality of reference, phenomena describing the same value or related storage location being frequently accessed. Okay, impact of memory bandwidth. Memory bandwidth is the rate at which data can be read from or stored into semiconductor memory by a processor. So memory bandwidth that is advertised for given memory system is usually the maximum theoretical bandwidth. In practice, the observed memory bandwidth will be less than, and it is guaranteed not to exceed the advertised bandwidth. Yang ni normal lah kan, apa benda yang advertise kat kita tak pernah yang betul kan. Contoh dia advertise limit speed internet bandwidth kita macam ni, actually tak sampai pun apa semua. Yang tu normal lah. So memory bandwidth is determined by bandwidth memory of a bus that as well as memory units. So memory bandwidth can be improved by increasing the size of the memory blocks, and the underlying system takes I times where I plus L time units, where L is the latency of the system to be delivered by B units, so that where B is the block size. Okay. Exploiting spatial and temporal locality in the application is critical for amortizing memory latency and increasing effective memory bandwidth. The ratio of the number of operation to a number of memory accesses is a good indicator of anticipated tolerance of memory bandwidth. Memory layout and organizing computation appropriately can make a significant impact on spatial and temporal locality. So kita akan stop sampai impact of memory bandwidth. Okay. So dalam ni untuk chapter tu ni banyak pasal dia punya architecture kita. So kita tengok implicit memory. Contoh dia. Okay. On the first slide kita tengok dia punya implicit parallelism. Kita tengok macam mana CPU actually works. So dia ada dia punya part mining, dia akan ada dia punya super scala, dia akan ada dia punya VLIW for example. Dan kita tengok daripada segi memory pula. Memory yang macam saya cakap second most important after CPU. Okay, kita tengok macam mana memory nak feed data, macam mana daripada segi bandwidth, macam mana dari segi dia punya latency. So impact of bandwidth and impact of latency in dia punya ni, right? So nanti kita akan sambung dengan alternate approach of hiding memory latency. Sebab latency ni sangat-sangat problem lah untuk computer science punya application. Sebab kalau ada latency, susah lah untuk kita nak buat kerja-kerja kita kan. Minta lambat, susah, right? Okay, so with that I will end my lecture for this week right here. So insyaAllah saya rasa minggu ni, hari ni belum ada task, tapi untuk hari yang seterusnya kita akan buat lab. So lab nanti saya akan bagi video lab lah. Alright, with that I will end my lecture here. So thank you for watching. Assalamualaikum.